In this problem, we will find the equilibrium constant of an oxidation-reduction reaction. So there are several equations that sort of relate equilibrium constant K, the E cell, which is cathode minus anode, it's the voltage of the battery. Also delta G at standard state, which is the free energy, whether the reaction is exergonic or endergonic. So this triangle that relates to 3 is kind of shown here. I got this from the Chang and Goldsby textbook. So here E cell is related to K, equilibrium constant. Here delta G at standard state, Gibbs free energy, is related to E cell. F is the Faraday constant. N is the number of moles of electrons being transferred during the oxidation reduction reaction. Here we have delta G, the free energy in standard state, being related to equilibrium constant K. Remember, products over reactants each raised to the stoichiometric coefficient. No solids, no liquids in K. So here is our oxidation reduction reaction. All right, let's go ahead and deconvolute this and get E cell. So here we have magnesium solid going to Mg plus 2, aqueous. So magnesium solid going to Mg plus 2. And let's balance this with 2 electrons to balance this out. And let's go ahead and get our reduction potential table to see how much voltage is associated with this half reaction. Let's see here. Here we go, magnesium. All right, so magnesium gains 2 electrons, and it's minus 2.37 volts. Here, magnesium loses those 2 electrons, so we got to flip it. So it's positive 2.37 volts. And then we have zinc plus 2 going to zinc solid. Okay, so zinc plus 2 going to zinc solid. And let's balance out the charge with 2 electrons. This is a reduction half reaction. So where is zinc here? Here is zinc. Okay, zinc going to zinc solid, gaining 2 electrons. That is minus 0.76 volts. So you have minus 0.76 volts. So this will help us compute E cell at standard state. So this would be E, let's see, you lost 2 electrons, so this would be E of the anode. Here you gain 2 electrons, so this would be E of the cathode. And the electrons cancel out with one another. And you're left with magnesium solid, basically the same equation that's written out in the problem set, plus zinc aqueous in water goes to zinc solid, plus Mg plus 2. So we basically split that reaction. This is the same thing that was given to us in the problem. But what's important to us is the E cell value. So positive 2.37 minus a 0.76. And let's see if I can do this on my calculator. I'm getting a value of 1.61 volts. And then let's use this equation here to get our equilibrium constant. I will use this one. We got E cell. R is our gas constant. T is the temperature. They tell us the temperature here in the problem is 25 degrees C. N is the number of electrons. It's a 2 electron transfer reaction. So 2 electrons are being transferred from manganese, gained by zinc plus 2. And R is the constant, F is the Faraday constant, which is 96,500 Coulomb over mole. Coulomb C is a unit of charge. So writing out this equation, E cell is going to equal to RT divided by NF, natural log of K. We're going to solve for equilibrium constant K for this reaction. It's actually at an equilibrium. It's a reaction that actually is spontaneous, so we would expect it to favor the product side. I say that because it's positive 1.61 volts. So E cell, we already figured out, is 1.61 volts. R here is 8.314 joules over mole Kelvin. Okay, I'll give that constant on the exam. T is 225 degrees C, which is the same thing as 298 Kelvin. N, this is a 2 electron transfer, N is 2. And F is 96,500 coulombs per mole, right? That times natural log of K. All right, so we got to take E But first, let's figure out all this mess here. So to get K, we have to take the inverse natural log, which is E. So here we have 8.314 times 298 divided by 2 times 96,500. And I'm getting 0.01283 or 0.01284. So let's take this and divide it over here so that it becomes 1.61 volts, okay, divided by this number here. You know, K has no units, so I'm not going to worry about units because natural log of K does not have units. Kelvin cancels, moles cancel, and Coulomb actually is joule over volt. But anyway, so that joule cancels out with that joule, this volt cancels out with that volt. It doesn't matter, you don't have to worry about units. So 1.61 divided by this whole thing, and the reason why you don't have to worry about units is because equilibrium constant has no units. So this whole thing is 0.01284. Okay, that equals natural log of K. So to get K, okay, I'm going to take the E of this value here, which is 1.61, divided by 0.01284. Okay, the or the inverse of the natural log. All right, so let's divide this by 1.61 and then flip it because it's 1.61 divided by this. So the flipping button is that. And then we will take the inverse natural log of that number, and we get a very large number of 2.94 times 10 to the 54, and that is our equilibrium constant for this reaction. Overwhelmingly favoring the product side. Two things that corroborate that is, number one, the extremely large value of the equilibrium constant, and the positive voltage. All those things are symbols that this reaction is heavily favored towards the product side of the redox reaction.